Okay, what is an electrolyte? Kyle said electrolyte is a compound that dissociates completely, or almost completely. Okay? That's a strong electrolyte. Now, are there some that don't dissociate completely, only dissociate partially? Yes, those are weak electrolytes. We use kind of the same definition for acids. A strong acid is one that dissociates effectively 100%. Of course, since it's a double-headed arrow, it's never exactly 100%. There's always some being back-formed, but for our purposes, we'll say it dissociates completely. What then is a weak acid? It's one that doesn't dissociate completely. Okay? So for strong acid, we will say we have complete dissociation. And for weak acid, we'll say we have incomplete. Or we could even say minimal dissociation. All right. Now, let's define those concepts in terms of equilibrium now. In an equilibrium reaction, the equilibrium in a strong acid will favor what? Products. Or the fancy word we just learned. Conjugates. Okay? So, a strong acid favors products or conjugates. And let's say equilibrium favors. Equilibrium favors conjugates, products. And what about a weak acid? Equilibrium will favor the original acid. Okay? Or react. Okay? Now, another point that kind of follows here, although it's not immediately obvious that it does. You can fill in the blanks here. Blank acids make blank conjugate bases. If we define these in terms of weak or strong, we can say this. Strong acids will make weak conjugate bases.
And the reverse is also true?
The reverse is also true. And vice versa. Okay? Strong acids make weak conjugate bases. Weak acids make strong conjugate bases. Also, although we're not talking about bases yet, we can make the same comparison there. Strong bases make weak conjugate acids. Weak bases make strong conjugate acids. So sum that up however you feel would be appropriate.
Strong bases are weak conjugate acids.
They are not weak conjugate acids. They make weak conjugate acids. Yes. It's an important distinction. Okay? Any questions on this? One of the things that we're going to do in this chapter is we're going to look at acid-base reactions more in terms of equilibrium. Which means we're going to have to introduce a constant, an equilibrium constant. Ka. Good. We're actually going to introduce 3 equilibrium constants in this chapter. Ka, Kb, and Kw. Well, they're all in the alphabet. That's something. All right, so let's talk about the acid dissociation constant. Once again, let's define our acid-base dissociation reaction. Okay. HA plus H2O, liquid, goes to form H3O plus A minus. All right? So if we were going to establish an equilibrium constant for this reaction, what would it involve? Well, take this reaction and let's make an equilibrium constant out of it. Equilibrium constant expression. What do we have to do? Would you like a hint? We'll start with this.
Concentration of the products.
Does this look familiar? Say it.
Concentration of the products to the power of their coefficients
Mm-hmm.
over the sum of the reactants.
So concentrations of products raised to the power of their coefficients over concentrations of reactants raised to the powers of their coefficients. So, what's the equilibrium expression Ka going to be then? Concentration of H3O plus, concentration of A minus, over what?
HA.
Concentration of HA times,
H2O.
why not H2O?
Because that is not natural. Oh, it's
It's a liquid. As with our previous equilibrium expressions, we only include the gaseous and aqueous phases. We don't include anything with solid or liquid. Okay? Now, if you happen to be working with what's called a monoprotic acid, in other words, an acid that only produces one H plus, these two quantities ought to be the same. And you shouldn't have to worry about exponents. This, however, could be different. Now, if we have a strong acid, tell me in just very general terms the value of Ka for that. In other words, don't give me a number necessarily, but describe what the number would be. It would be the total value of Ka. First of all, what's going to be present in the largest quantity for a strong acid? These or these? Which, for a strong acid, which is present in the greatest quantity? The products, right? So, these values are going to be comparatively large. This value we don't care about. What about this value? Small. So if you have a comparatively large value times a comparatively large value divided by a comparatively small value, this is going to be a large value for strong acids. And in fact, as this approaches 0, those of you who do a calculus, what happens to this value? It approaches infinity. So, the published dissociation constants, Kas, for strong acids, frequently just say very large. They don't even have a number associated with them. But if you see very large, that tells you, hey, this is a strong acid. This dissociates effectively 100%.